Oh, thank you. So, almost 45 years ago, Bekenstein and Hawking showed us that black holes are thermodynamic objects with characteristic temperatures and entropies. And I think it's fair to say that the quantum gravity community has not yet recovered from that. Black hole thermodynamics is a beautiful subject, but it's also a very puzzling one. Some of the puzzles are famous, for instance, the information loss problem. Others are a little less famous, but still present us with very interesting puzzles that might tell us something about the fundamental nature of quantum gravity. The puzzle that I'm going to talk about is something that's often called the problem of universality of black hole entropy. And I'll explain that in a minute. But let me first say, for those of you who have heard me talk about black hole entropy before, this is a puzzle that I've been fretting over for, probably about 20 years now. And I have given other talks here and elsewhere about this. There's something new here, so before you start falling asleep, try to hold on. I'll try to explain why there is a new result which I think resolves many of the problems of previous approaches. So let me start by explaining the problem a little bit. There are actually two separate problems that are called the problem of universality in black hole physics that are logically independent, although their solutions may be related. The first has to do with the very simple and universal form of the Bekenstein-Hawking entropy for black holes. Now, if we had been told that the entropy for a Schwarzschild black hole or the entropy for an extremal charged black hole was a quarter of the area, we would have said, well, that's something interesting about the Schwarzschild black hole or about extremal black holes, and we should try to understand why it's exactly a quarter of the area. But actually, we're told something much more than that. Start with a black hole, a black string, a black ring, a black brane of any dimension, a black Saturn, a black hole with a black ring around it. In any dimension where these objects exist, give them any spins you want, give them any charges you want under any long-range gauge fields. Distort the event horizons any way you want by putting other lumps of matter nearby and ask what's the entropy. And it's still a quarter of the horizon area in Planck units. So this is presumably telling us that this formula is not just about this black hole or that black hole, but is about properties of horizons in general. The only way that I know of to change this result is to change the gravitational action. And when you do that, you still get a nice universal equation with some integral over the horizon. It's just that the details depend on exactly what you put into the action. So that's version 1. Version 2 of the problem of universality is, I guess you could say that it is trying to understand why version 1 is so easy to solve, in the sense that it is so easy to find programs in quantum gravity that give you the right answer. So we certainly don't have a theory of quantum gravity at this point, but we have a bunch of different research programs that are developed enough that one can start asking about black hole entropy. And so what do we find? We find that in string theory, we can explain the area law for entropy in at least 2, probably 3 different ways that are not obviously related. In loop quantum gravity, we can explain the result using 3 different approaches, which are, again, not obviously the same. We can understand black hole entropy as entanglement entropy across the horizon with various approaches to dealing with cutoffs. We can look at Sakharov's old idea of induced gravity, where the Einstein-Hilbert action comes from integrating out heavy fields, go back and count the degrees of freedom of the heavy fields. That gives us the black hole entropy. We can do instanton calculations. For example, we can determine the entropy by looking at the volume of phase space available for creation of black hole pairs. We can write down topological formulas for black hole entropy that just look at the topology of the Euclidean sector. Or we can go back to Hawking's original derivation, which didn't refer to quantum gravity at all, but only to fixed black hole background and quantum fields. None of these is remotely complete. But within the realms in which these proposals do make sense, they all give the right answer. Now, if you're a cynic, you'll say, well, of course they give the right answer because we know what the answer is supposed to be, and you don't publish a paper unless you get the right answer. But there's more to it than that. Let me give one particular example of this. Take the cleanest derivation in string theory, which is the Strominger-Vafa derivation of the entropy of extremal black holes. The way that derivation works is that I say, tell me the entropy of an extremal charged black hole in 5 dimensions with 3 kinds of charges. And so what you do is 3 separate steps. First step, you take those charges, you look at a system of weakly coupled strings and branes with those charges. You calculate the entropy by looking at the degrees of freedom of this weakly coupled system, which you know how to handle. Then you take the same, and you express the number of degrees of freedom in terms of the charges. Then you take the same charges and you look for the strongly coupled black hole that has those same charges. You figure out the horizon area and you write that in terms of the charges. Then you look at those 2 results and you say, look, the entropy of the black hole is 1/4 of the area. And then I say, oh, did I say 5 dimensions? I meant 6. And while you're at it, could you throw in an extra charge? You can't say, well, it's 1/4 of the area. What you have to do is go back and recalculate the degrees of freedom of the weakly coupled theory, find the black hole solution, calculate its area in terms of the charges, and then you say, oh, look, it's 1/4 of the area. Then I say, how about 7 dimensions? And eventually you get sick of it and tell me to stop asking. But there is clearly some underlying structure here that's missing. And I think that's what both of these versions of universality are telling us, that there is some simple structure involved with the nature of horizons that determines the black hole entropy independent of most of the other details.
Just as an interjection, since slide 1 said correctly that the universality issue is contingent on the choice of gravitational action to get something different for Lovelock theories, for example. How far along are these arguments for higher curvature theories? Doing counting and not getting the area, but if getting
So for string theory things, for the first 2 versions of string theory and possibly the fuzzball approach, things are pretty far along in getting the general
So you can get
walled. Yeah. For loop quantum gravity, as far as I know, the only cases that I know deal with the standard Einstein-Hilbert action. Same for induced gravity. Instant time calculations, I think, can be more general. Entanglement entropy, there are some more general results. So it's mixed. Okay, so there is perhaps some deeper structure here, and we should be looking for it, especially because if black hole entropy is anything like ordinary entropy, understanding it is telling us something about quantum gravitational degrees of freedom. So an obvious first guess is that the proportionality of entropy to area means that the degrees of freedom are associated with the horizon. And that's an old idea that goes back to Bekenstein's first paper. But it's not enough. It might explain the proportionality to area, but it certainly doesn't explain the universality of the factor of a quarter. The next version of this kind of argument is the proposal that there is a symmetry associated with the horizon that determines the entropy. Now, that's a lot to ask of a symmetry, but there is, until recently, there's been one case in which we know that that's possible. That's a two-dimensional conformal symmetry, which has the same kind of universality properties, that if you're just given a couple of simple parameters of that symmetry, that's enough to determine the asymptotic density of states, or the entropy. For the three-dimensional BTZ black hole, Strominger and independently Birmingham, Sachs, and Sen showed in 1998 that this works, although they dealt with the symmetry at infinity rather than at the horizon. But in 3 dimensions, that doesn't really matter so much because there aren't any gravitational degrees of freedom between infinity and the horizon. And immediately after that, a bunch of people, including me, tried to generalize these results to arbitrary dimensions. And we had some success. It can sort of be done. You can find a conformal symmetry near the horizon that has the right properties. But the results have always looked a little bit artificial. It has always taken some pounding to get the symmetry into the right form. These methods have also generically had some flaws that haven't exactly been fatal, but have been uncomfortable. They usually require a symmetry either at infinity, which can't distinguish between a black hole and a star, for instance, or at a stretched horizon, someplace just outside the horizon. Typically, when you start with a stretched horizon and then take the limit as you go to the horizon, the limit isn't always unique, and various parameters blow up in that limit in a way that leaves the entropy finite, but means that the symmetry no longer quite makes sense at the horizon. In addition, these standard approaches, or these existing approaches, I don't want to claim they're standard, have failed miserably for what ought to be the simplest case, which is the two-dimensional dilettante black hole. And for higher dimensional black holes, they've had a similar problem, which is that morally, the symmetry ought to just depend on the null generators of the horizon. But in practice, you always have to put in some extra angular dependence just to make things work. So things have looked a little bit awkward. What I want to try to show you today is that all of these problems can be avoided, that there's really a much cleaner way of getting a symmetry that is actually at the horizon, that's well behaved, and that gives you the correct entropy. The key new ingredient was the recent discovery that two-dimensional conformal symmetry is not the only symmetry that is powerful enough to determine the density of states. That the same thing can be done for a symmetry called BMS symmetry. Now, BMS symmetry, for those of you who are unfamiliar with this, is a symmetry that was originally discovered as an asymptotic symmetry at null infinity of asymptotically flat black holes. I want to emphasize that the symmetry that I'm talking about here is not that. It's a symmetry at the horizon, but it's one that happens to have the same group structure as a BMS symmetry. So the relationship with asymptotically flat three-dimensional black holes is a coincidence, but it's a useful one because that's the context in which people figured out how to count the states. So that's the main ingredient. The other ingredient that I'll be using is what's called covariant canonical formalism, which is a nice, elegant way of expressing a symplectic structure that allows you to write everything directly on the horizon, which is often difficult because the horizon is a null surface. So, some more details now. Start with a black hole in arbitrary dimensions. Near the horizon, you can at least almost always perform a dimensional reduction in which you just keep the radial and time directions and treat the transverse directions in a Kaluza-Klein kind of way. What this gives you is two-dimensional dilettante gravity. The action looks like the ordinary Einstein-Hilbert action, but with an extra scalar field, the dilettante, which has some potential, which depends on what theory you started with and exactly how you do the dimensional reduction. Morally, what this dilettante is the transverse area of the horizon, or of the region near the horizon, the area in the directions that you've dimensionally reduced. In two-dimensional dilettante gravity, the Penrose diagram looks just like it does for any other black hole. Here I've drawn the exterior section for an asymptotically flat black hole, but for the rest of this argument, the details of what happens at infinity are unimportant. This works just as well for an asymptotically de Sitter or asymptotically anti-de Sitter black hole. I am going to write things in terms of a pair of null vectors, L and N, where L is chosen so that at the horizon it is the null normal of the horizon, and where N, just for convenience, is normalized to have a divergence of 0. This lets you continue these null vectors away from the horizon in a nice, simple way. Later on, I'm going to need a Cauchy surface, or a partial Cauchy surface, and I'm going to choose that to be the horizon and future null infinity. So the action for dilettante gravity in terms of these null vectors takes some very simple form. The equations of motion are fairly standard. That's That's the starting point. Now, in order to talk about horizons and symmetries of horizons in this setting, we're going to need a definition of exactly what we mean by a horizon. And that is, we're going to need boundary conditions that we set at the horizon.
Sorry, in your formula, go back once.
Yeah.
What that scalar curvature is, which scalar curvature?
That's the two-dimensional scalar curvature. Everything here is two-dimensional.
So scalar curvature of which surface?
It's a two-dimensional manifold, so it's the scalar curvature of the two-dimensional manifold.
The space-time.
It's a space-time.
Or just two space-time
Oh,
dimensions.
this whole thing is still just two dimensions.
1 plus
Right.
Oh, I thought you were doing a dimensional reduction.
No, well, I'm saying I've already done the dimensional reduction, and when I've done that, I end up with this as the two-dimensional action. Plus, in general, a bunch of other fields that come from Kaluza-Klein reduction of everything else, but that turn out to be irrelevant for the calculations of the entropy.
Is there a kinetic term for phi in the action?
Is there a kinetic?
Interaction in the first expression
Yeah.
for the action. Is there no kinetic term for phi?
You can always, in two dimensions, you can always absorb the kinetic term by a rescaling of the metric, and I've done that. It is, again, not necessary and doesn't make a difference to the final results or to the equations of motion for that matter, but it just makes it a little bit easier to do the calculations.
Can we infer from two-dimensional physics what is valid in fourth dimension?
The two-dimensional action here is one that is obtained by starting from 4 dimensions and essentially integrating out the degrees of freedom starting in n dimensions and integrating out the degrees of freedom in all but 2 dimensions. Physically, near the event horizon of a black hole, that retains most of the information. The basic reason for this is that when you're near the horizon, if you look at a stationary observer near a black hole horizon, the transverse degrees of freedom get redshifted away so that only the degrees of freedom in the, roughly speaking, the RT plane are important.
That's for spherical symmetry.
No, it's generic. What you mean by the RT plane here is a plane determined by the killing vector that generates the horizon and a second vector, which is the divergence of the square of that killing vector. That gives you 2 preferred dimensions, and you can show pretty generic.
Contain information about the rotation of the black hole?
Oh, yeah. Yes, the 2 dimensions here, if you have a rotating black hole, this L is really the generator of the horizon in the higher dimensions. So, yeah, if you like, it's a co-rotating frame near the horizon.
Multiple rotations.
Yeah.
Sorry, just a check. You said the divergence of the square, the first vector is null.
Yeah.
So the square is 0. So what am I?
You look at the killing vector. The killing vector is null at the horizon, but it's not null away from the horizon.
Okay.
Right. I mean, the horizon.
Killing vector throughout the whole. At least
Right.
linear.
For a rotating black hole, you take the killing vector of the space-time. For the rotating black hole, for a stationary rotating black hole, the horizon is generated by a killing vector which can be extended off the horizon as a killing vector. That killing vector is null on the horizon, but it's not null off the horizon. And you take it square, the divergence of that gives you a vector that is that's basically normal to the killing vector. And it gives you a nice local dyad.
Although dynamics, two-dimensional physics, quite different.
Oh, yeah.
Except for gravity, rather complicated knowledge.
Right.
This
So,
must affect the result.
this is the entropy is a property of a stationary, or at least quasi-stationary black hole. There are additional quantum contributions to the entropy from modes of all of the other fields, including the modes of the gravitational fields from the higher dimensions. The usual argument, and I don't have much more to say about it than this, is that those same corrections also renormalize Newton's constant in such a way that that the contribution to the that the area law remains the same, that the renormalization of Newton's constant compensates for the renormalization of the entropy. It's certainly true that for a rapidly changing black hole, this argument would not work, but it's not entirely clear what the entropy would mean in that context either. Raphael?
I think you more or less answered. So in effect, we're kind of perturbing about the stationary
Yeah.
black hole.
Mm-hmm.
I mean, there is reason to believe that the area is correct, even far away from stationary. The most,
Yeah.
I think, the most cogent one is the area increase law
Mm-hmm.
in the classical theory.
Right.
But there are also some calculated in causal sets of non-stationary black holes where one gets area also.
Yeah, so I would love to be able to generalize this to dynamical horizons. I'll say a little bit about that at the end. Other questions? Okay, so we next need boundary conditions at the horizon. So let me, just for notation, define capital D to be just a covariant derivative along this null vector that generates the horizon. And equal with a delta sign above it means equal at the horizon. So what features do I want to preserve at the horizon? First of all, I would like to preserve the fact that it's horizon, that the area is not changing as you move along the horizon. As I said, the dilettante phi is the remnant in the dimensionally reduced theory of the transverse area. So that condition, basically the condition that it's a non-expanding horizon, is that d of phi is 0 at the horizon. Next, I would like to impose that the geometry is also stationary at the horizon. In 2 dimensions, the geometry is entirely captured by the scalar curvature. So the condition there is that the derivative of the scalar curvature along the horizon is 0. Then finally, basically as a way of making the calculation simpler, I choose to fix the conformal class of the metric at the horizon. This can be generalized. I'm in the process of figuring out the greatest generalization. But for now, some pieces of this are necessary in order to have the covariant canonical formalism well defined. But for now, it's just simplification.
What do you mean when you say you're fixing it? What exactly are you doing?
I am going to be looking at variations of the metric, and in particular symmetries, that are restricted to not change the conformal class of the metric.
So symmetries
At
that
the
don't
horizon.
rescale the metric by a conformal factor.
No, symmetries that do rescale the metric by a conformal factor, but that only do that don't change the conformal class. So, for instance, diffeomorphisms don't fit that, but a diffeomorphism combined with a suitable local Lorentz transformation, a diffeomorphism along the horizon combined with a local Lorentz transformation actually will preserve the conformal class. Yeah.
So, but in 2 dimensions, the metric can always be put into a conformally flat form.
Right.
So do you mean by that you are changing only the conformal factor and leaving it flat? I mean, leaving it...
Yes, or not necessarily conformal. I'm choosing some particular conformal class and then looking at symmetries, but yeah. Not necessarily flat. I could do that, but that's...
So you really need all metrics, or G nu is e to the phi, G fixed.
Yeah.
That's what you mean.
Yes.
So this is the 4-dimensional metric?
No, this is, everything here is 2-dimensional. The reference to 4 dimensions was just to justify the dilettante action, and everything from now on is in 2 dimensions.
Isn't that very weak assumption though? Because always uniformize.
Yeah. Well,
No, I think
it depends on, you can always choose the metric. You can always perform a diffeomorphism that makes the metric conformally flat. But that diffeomorphism, I want to restrict to diffeomorphisms that preserve the horizon. And you can't necessarily always make the metric conformally flat at the horizon with a diffeomorphism that preserves the horizon. So it's a slight restriction on what additional diffeomorphisms are allowed.
Can you say some invariants that, sort of necessary and sufficient? Like if you were doing a torus or something, that there's some simple invariants that define the conformal class.
I want to know, because I don't want to choose a particular conformal class. I only want to say that once I'm looking at a metric in a particular conformal class, I am going to restrict myself to transformations that don't move out of that conformal class.
Right, I know, but there might be some invariant. It might be another way of saying it, like in such and such an invariant that my transformation has to preserve.
Let me think about that. There is something called the cotton tensor, and that characterizes the conformal class of a... Well, no, that's 3-dimensional. 2-dimensional.
Because the diffeomorphisms don't change. If you need geometric invariants, the diffeomorphisms don't change it.
Right.
So you're talking about somehow the form of the metric.
Yeah.
The form of the metric is some conformal factor times, say, delta alpha, or A of mu or something.
Right.
It's not changing.
Yeah. This...
You can come back.
Yeah, let me go on, because you'll see more specifically what I mean when I talk about the transformations I'm looking at. So given these conditions, the question is what are the symmetries of the action that preserve those boundary conditions at a horizon? And one obvious such symmetry is diffeomorphisms that are, I guess the proper way to say this is that are normal to the horizon, at the horizon, which always gets confusing because the normal to a null surface is tangent to the null surface. But so diffeomorphisms that preserve the horizon but move you along. So those are diffeomorphisms generated by vector fields proportional to this vector LA near the horizon. And so you can work out what the transformations are of the metric and the dilettante under such a diffeomorphism. And if you have this additional condition that the derivative of the parameter along the other null direction is 0, then the diffeomorphism is a Weyl transformation of the metric, so it preserves the conformal class. So that's the obvious symmetry, and it's the only exact symmetry. But there is another approximate symmetry that can be made arbitrarily good near the horizon. And this is a shift symmetry of the dilettante. So if you look at a shift of the dilettante by a divergence of a vector proportional to LA, and just ignore the change in the metric for now. If you just look at the shift, such a shift of the dilettante, you go back to the action. You can always do an integration by parts, which moves the derivative to act either on phi or on r. But our boundary conditions are that d phi is 0 and dr is 0 at the horizon. And so if you choose the parameter eta to fall off fast enough away from the horizon, that is, if you look at shifts of the dilettante that are localized very close to the horizon, you can make the change in the action arbitrarily small. There is a technical detail here, which is the reason for this extra term, which is that the shift in the dilettante moves the horizon a little bit. You need, to preserve the condition that the scalar curvature at the horizon doesn't change, you need an extra diffeomorphism that moves the horizon back to its original place, and that requires, in turn, an additional small conformal transformation of the metric. But again, this is a transformation. It's a rescaling of the metric, which is 0 at the horizon, and if the parameter falls off fast enough, this is arbitrarily close to a symmetry.
And the claim is that if I add a surface term so that I get a one direction principle including at the horizon, this is all fine?
Mm-hmm. Yeah. Actually, that will come in when I talk about the covariant canonical formalism, which naturally is basically a formalism about the surface terms.
Can you say what is this geometry? If we go back to 4 dimensions, what are we doing?
So it is. I don't have a complete answer to that. Roughly speaking, what it is a particular conformal rescaling of the metric, of the whole metric, combined with a diffeomorphism that removes the rescaling from the R and T components. Roughly speaking, what this looks like in 4 dimensions is if you have a stationary black hole with a killing vector chi A, and you look at a transformation a conformal transformation of this sort. When you stick this variation, I guess I should say that's the variation. When you stick this variation into the Einstein-Hilbert action, you can integrate by parts and you get the derivative along the killing vector of the scalar curvature, which is 0 because it's a killing vector. Now, it gets tricky because the new metric no longer has a killing vector, and so I'm trying to understand better exactly what this means in 4 dimensions. But it is something of this sort combined with an appropriate diffeomorphism. Other questions? Yes, as I'll say at the end, one of the big remaining problems is to actually completely lift this to higher dimensions. And I have some ideas, but I don't know how to do that yet. Okay, so a little diversion next. We're actually almost finished, given these symmetries. But I want to describe everything in the covariant canonical formalism. So let me give a brief introduction to this for those of you who aren't familiar with this. The basic idea, which I'm told goes back to Lagrange, is that if you have a theory that has a good initial value problem, then the phase space is isomorphic to the space of solutions of the theory. And the isomorphism isn't canonical. The way that you carry this out is you pick a time slice, then given a point in the phase space, that's a position and momentum, you use that as initial data on your time slice. That gives you a classical solution. Given a classical solution, you look at the position and momentum it determines on your time slice. That gives you a point in phase space. So it's a nice isomorphism that allows you to do Hamiltonian formalism in a nice covariant way on the space of classical solutions. That means, in particular, you can define a symplectic form on the space of solutions. You can define a Hamiltonian on the space of solutions. As a simple example for the symplectic form, if you start with just a point particle and you look at the variation of the action, you end up with a surface term, which is P delta Q. If you think of delta as meaning an exterior derivative on the space of solutions, then this is a one form on the space of solutions. If you take its exterior derivative, you get delta P wedge delta Q. That's a standard symplectic form. The same thing works if you start in the Lagrangian form. You would still get a boundary term that looks like Q dot delta Q. And again, that tells you what the canonical pairs are. It gives you the symplectic form. For field theories, the same thing works fine. It's just that instead of just getting something like this, you get an expression like this integrated over a Cauchy surface. You can then define a Hamiltonian. The technical definition is that given a one-parameter family of transformations, the Hamiltonian is the thing whose variation gives you the symplectic form acting on that with that transformation as one of the arguments. This is very unobvious looking, but if you write everything in terms of the fields and functional derivatives, this is just Hamilton's equations of motion, that the variation of the field is the symplectic form times the derivative of the Hamiltonian with respect to the field. So this is q dot equals dh dp, and so on. It's worth mentioning, emphasizing really, that this equation doesn't always have a solution. You can write down transformations that simply don't have a Hamiltonian that generates them. Those that do have a Hamiltonian are called integrable, and it's not at all obvious whether, if I just give you a transformation, it's not obvious whether it's integrable or not. So now, let's apply this to the system of dilettante gravity. As I said, I'm going to choose as my Cauchy surface the future horizon and Scri plus, future null infinity. But since I'm looking at transformations that are localized very near the horizon, the contribution from null infinity is unimportant. And so really all that matters is an integral along the horizon. I can write down the symplectic form just by looking at the variation of the dilettante action. What it tells me is that the dilettante, which is basically the horizon area, is conjugate to the surface gravity, which is something that we knew already from a bunch of other ways of getting at this. It is known that the diffeomorphisms are integrable in this formalism, that you can write down a Hamiltonian. It's much less obvious that these shifts of the dilettante near the horizon are integral, but it turns out that they are, with a lot of nice cancellations that didn't have to be there, but really are there. And so you can write down generators of the two transformations, and since you have the symplectic form, you can look at their Poisson brackets to get the algebra of the symmetries. Yes?
When you say integrable, is that the same as just preserving the symplectic structure, or is there more to it?
It means that there is a Hamiltonian that generates those symmetries.
Is that more than preserving?
Yeah, it is more than preserving the symplectic structure. It's saying that delta squared. So I guess it's saying that that an arbitrary variation of the symplectic form here is 0. I think that's more than preserving the symplectic structure.
I think only below. It's like quadratics there.
Yeah. Okay, so you can write down the commutators, or the Poisson brackets, as I said. The general formalism gives you those in terms of the symplectic form. You work these out for dilettante gravity. You get an algebra of this sort, which if you had spent the past few months looking at three-dimensional asymptotically flat spacetimes, you would have recognized, as I did, is the algebra of the three-dimensional BMS symmetry. Although, as I said, this has nothing to do with asymptotically flat three-dimensional black holes per se anymore. But it's an algebra that you can recognize. It has a central extension. And now you look at the recent work of Bagchi and collaborators. As I said at the beginning, we've known for a long time, or since 1986, that if you have a two-dimensional conformal symmetry, that's enough to determine the asymptotic density of states. And what Bagchi et al. Showed is that there's a generalization of this to a theory that has a BMS3 symmetry. There's a formula for the entropy in terms of the central charge and various weights, the eigenvalues of L0 and M0. You calculate those for the black hole. It's fairly straightforward. Stick them into the formula, and you get an entropy, which is the area of the horizon, the dilettante value at the horizon, divided by 4 in Planck units. So you get the Bekenstein-Hawking entropy as a fairly general result that doesn't depend, for example, on the nature of the dilettante potential, doesn't depend on any other fields that you've stuck into the action. They just don't contribute at this, to this calculation. And doesn't depend on the details of what higher dimensional theory you started with that you dimensionally reduced to get this dilettante action. That affects the value of the potential and the other fields, but those don't matter. So this is at least a first step towards a general derivation of the Bekenstein-Hawking entropy as a number of states. This is directly a count of the states in representations of this symmetry in a way that is at least moderately universal, that doesn't depend on any of the obvious details. Yeah.
Go back one slide.
Mm-hmm.
Somehow you expanded out. What is this LM and LM?
Oh, so I just
expanded out
expanded.
phi somehow.
Yeah, I expanded. I just took a mode expansion. You can define.
The mode in which, which mode?
Oh, okay. So you have this null vector L on the horizon. There is a natural sort of dual coordinate in advanced time, such that LA del A V equals 1. You expand in modes in V.
So these are expanding out along the generator.
It's along the generator of the horizon. So this is all genuinely at the horizon.
So the central charge is like 1 over G, but if you go to the next slide,
Mm-hmm.
you've got the square root of 1 over G. So one of those H's has got to go like G or root G or something.
Yeah,
right?
yes.
That's what happens, basically.
Yes, that's what happened. Basically what happens, so these are classical Poisson brackets. If you want to turn them into commutators, the commutators have extra factors of H bar, which is good. That means that the central charge picks up a factor of 1 over H bar, which is basically where the H bar and the Bekenstein-Hawking entropy comes from. It comes from the fact that a classical central charge gives you a quantum contribution that goes as 1 over H bar.
So it's a step in making this quantum to use the
Right.
results of the other people.
Yes, absolutely. Yeah.
So, just the first one looks like the usual width algebra. So is that also correctly the composition or central extension?
There are possible central extensions here, but they are smaller by factors of H bar.
Actually,
So
that's the only central charge.
this is the only classical central charge, just from a direct computation of the Poisson brackets. There are quantum corrections. They are, if the Bekenstein-Hawking entropy is order 1 over H bar, the quantum corrections to the central charges, and there also is potentially a central charge there and there. but the quantum corrections all give entropy corrections of order 1 rather than 1 over h bar. Yeah.
So it's a partial answer, what you just said, it's a partial answer to my question. So in the old days, people, there were no atoms, right? So to have this symmetry in people, one which was you, I think, would argue that you have L's, and I guess you would be quantized if you get a central charge, and that was what was giving the entropy. Was that
well, no. I mean, we always knew that there had to be a classical central charge in order to get the 1 over h bar in the Bekenstein-Hawking entropy. So there was always a... So what we always did was stuck in another diffeomorphism. As I said, the previous stuff absolutely failed in 2 dimensions. But in more than 2 dimensions, you can stick in another diffeomorphism, say along an angular direction, and you can argue that you can fix boundary conditions in such a way that the diffeomorphisms you're interested are not independent, and you can cook things up in a way that gives you a central charge.
But then why can't you apply those arguments in higher dimensions for this?
Because you only have one diffeomorphism that preserves the horizon. Right? You only have the L's.
If I go to higher dimensions.
Yes. In higher dimensions, you can cook up extra symmetries.
Yeah.
They aren't there in 2 dimensions.
No, I know. But
Yeah.
in higher dimensions,
Right.
you could presumably play the same game. So then why would I not argue that I'll get something else in higher dimensions?
Okay.
Or at least that I could cook something else up.
You probably could cook something else up.
I mean, I know
What I
the right
would-
answer, so we don't want to.
Well, no.
I mean,
So what I would argue, what I would argue is that physically, what you ought to be looking for is transformations that are just along the null generators that generate the horizon. Because those are the only things that are uniquely picked out and uniquely characterize the horizon. If you know the null generators, you know the horizon. And everything else there is just sort of carried along. And so one of the things I had on the first or second slide as one of the uncomfortable features of previous derivations was the fact that for them to work, you had to not just look at the null generators, but you had to add an extra kind of arbitrary angular dependence, just to get any symmetry that had a reasonable algebra at all.
So now you're saying the happy users don't need to do that anymore.
Yeah, you don't need to do that anymore. You don't have to do these sort of artificial-looking things to force your symmetry into the form that you want it to be. This is just the symmetry. It works for the 2-dimensional case where previous approaches just didn't work at all, and it's a symmetry of the horizon, while with previous approaches you needed to look at symmetries of stretched horizons and then wave your hands about the limits. So this is all my own work that I'm now making fun of. But it's nice that, I mean, and some others, but a lot of it's mine. But it's nice to actually have something that seems to work without extra arbitrary assumptions, I think. Of course, I believed that before in the past, so. Yes?
On the next slide, are you going to tell us more about what the values of these H's are and what the miracle is that generates the
Well, I wasn't going to, but I can. I mean, they're all if you look at these expressions for the generators, it's basically just a matter of doing some straightforward calculations. You have a mode expansion. You want these evaluated at the zero mode. For M, it's simple. You just have minus 1/2 kappa squared times the zero mode. The normalization of the zero mode is fixed just from the requirement that the algebra looks just from the normalization that you get these m minus n's here without additional factors that fixes the normalization of the modes. So for M, it's just a straightforward calculation. For L, it's a little bit trickier. For L, there is a boundary term to the generator, which is here. But again, it's just a matter of looking at the algebra and seeing what you need to have a well-defined variation of the generator, and you get a corner term. You evaluate it at the zero mode, you get some number.
So what here? Now, suppose you have a null surface, and you have a symmetry to have the structure. So you get the same answer for the white hole horizon or feature or path now.
You get the same answer for the white hole horizon. For null infinity, I think you don't, because the boundary conditions that I used include that the area is constant. And I don't know if future...
0 over 0 there or something.
Yeah, so I haven't looked at this at null infinity, but certainly I think that you would need different boundary conditions, and so it's not obvious to me, at least.
But if I think of it from the compactified terms construction, the area, I think the area is also a station.
Is it?
I'm not sure.
I'm not sure. I think, I'm not sure. I don't know enough about null infinity. Yeah.
To extend this to Vaija to get a time-dependent entropy in some sense?
It ought to be possible, but I haven't done that yet. Let me get to my list of next things to do, which will probably include something like that. No, doesn't. So there should be an additional bullet point here, which is to look at what happens with slowly varying dynamical horizons. But so the things on my list, at least, are, as I said, I had chosen to limit to transformations that fixed the conformal class of the metric, basically because that was good enough and it made everything look simple. But it would be nice to find the most general class for which, the most general set of variations for which the covariant canonical formalism made sense. As I've been saying, it would be nice to lift this explicitly to higher dimensions. If this is a universal explanation, then all of those items that I listed in some earlier slide of different ways of deriving the entropy from different approaches to quantum gravity should have something like this hidden in them somewhere. And for a couple of cases, I think I know how to pry that out for the ADS-CFT correspondence for for horizons that look locally like BTZ. There's at least something vaguely like this that you can see, and also for the induced gravity, there's something, again, vaguely like this that ought to be possible to make more explicit. And then, well, this isn't exactly what you were saying, but it's related. In order to look at dynamical black holes, you really have to couple to matter. And that's potentially very interesting because what the entropy that I get here depends on just some parameters and a central charge. If you couple to quantum matter, the quantum matter also has some central charge, and there are results about the flows of central charges between conformal field theories, at least, that should be generalizable to this BMS version. What I dream of is showing that the evaporation of a black hole corresponds to a flow in a conformal field theory in which the central charge of the black hole is going down, which decreases its area while the central charge of the matter is going up. That's just a pipe dream at this point, but that's the thing that I think would make this really, make many people believe, okay, this is really not just an interesting answer, but the right one.
Tonight in the bistro, so everybody's welcome to join. Any more questions for Steve? John?
Probably a inappropriate question. Ultimately, we rely on experimental physics to determine whether the theories are correct. The question is whether it's possible observations entirely the veracity of these ideas. For example, the black hole has very well thought of things. So we have a gravitational wave result. We have the randomized telescope observations coming out of the problem is that studies show that a lot of times it needs to be close to that. So this boxes indeed, if there is a horizon, it's very easy.
Yep.
And so it's important to expand the observations from this situation.
Yeah. Yes, there are some fairly exotic proposals for changes of the near horizon structure of black holes that, at least there have been some recent claims that they could potentially be observed in future gravitational wave observations. For instance, if you have changes that change the quasi-normal mode structure. But yes, it's definitely a real problem, and it would be wonderful to have a little black hole that you could put in a laboratory and watch it radiate, but I'm not holding my breath on that one, although some people who worked on the LHC were at one point. Yeah, wish I had something useful to say about some new possible observation or observational test of any of this at this point. I don't.
Okay, so I don't know other questions or comments for Steve. Given the view of time, let's thank Steve again.